So, uh, so our speaker today is Rowen of Bar-Ilan University, and he will speak on weakly primitive axial algebras. Please, please.
Well, thank you very much. Um, this work is heavily influenced by this seminal paper of Rowen and Spektorov, in which they considered axial algebras of Jordan type, primitive axial algebras of Jordan type. And Yoav Segev, who's my constant co-worker in this, and I have tried to find the setting in which one could, the algebraic setting in which one can obtain a suitable algebraic theory in the most general possible way without giving up on a robust theory. So I just want to remind you, probably you all know more about axial algebras than I do, but nevertheless, an axis is a idempotent which satisfies this amount of associativity. And primitive means that the one eigenspace from both the left and right is just the one-dimensional space generated by the idempotent. And of course, this whole thing started with Albert, I think. Now, so in the HR, I'm going to call the whole Spektorov paper HRS just for ease of saying it. And only one eigenvalue was allowed other than 0 and 1. And we want to consider several eigenvalues. But but we have to restrict our fusion rules in order to be able to say something. Okay. And there are other examples that come up, such as semigroup algebras. Okay. So let's go on to the terminology. A will always be an algebra, and we have left multiplication and right multiplication. And an axis, as I said before, has left multiplication commuting with right multiplication. That's the definition of an axis. And so we'll have the set of left eigenvalues and right eigenvalues, and then we'll take their product to be S. And if A is an axis, then the algebra, big A, decomposes as a direct sum of the eigenspaces, of the two-sided eigenspaces. Now, 1, of course, is a special eigenvalue because A is a 1, 1 eigenvector. And 0 also plays an important role. I guess if you have an algebra with unity, then 1 minus A would be, but we don't assume the algebras have unity. So, okay, so we're going to call S of A the set of eigenvalues, possible paired eigenvalues of A. Okay, and when it's the eigenvalue is the same on the left and the right, we just call it by one symbol instead of two. Okay. So A decomposes as a direct sum of eigenspaces. This is just what I said before. Of paired eigenspaces, that is. And so just for terminology, we're going to call A an S-axis to emphasize the set of eigenvalues other than 0 and 1. And we're going to use this notation. y1 plus y0 plus ys. That's the decomposition. Okay. A possibility among y1 is some multiple of a. So we'll get back to that. And so I hope try to remember this terminology. S circle is the set of paired eigenvalues which have non-trivial eigenspaces. S dagger is the non-commutative part, where mu is not equal to nu. And S bar is the set, well, it's a set of eigenvectors whose square is not zero, but I don't think we're going to use that. And then S tilde will be the complement. From instead of mu nu, we put mu mu. Okay. And S bracket is S with its complement. Okay. So we have a mu left axis and a nu right axis. Okay. Absolute value 1 axis is an axis such that the set of eigenvalues other than 0 and 1 has order 1. And so in particular, S could be a pair mu nu, and then we'll call it a mu nu axis. Okay, and then if we use squiggly brackets, we're permitting either this or reversing. Okay, so is the notation okay? It's a lot of notation, but if you have any problem, please just stop me if I'm using too much notation. So for example, for bracket mu nu axis, A would be this. Okay, an S-axis is commutative if all its eigenvalues are mu equals nu. And this implies that A commutes with all the elements of A. Otherwise, we say little a is non-commutative. So I guess the new thing in this study is to try to look at non-commutative axes. Okay. And actually, Yoav and I did look at non-commutative axes, but only with a single eigenvalue. So now we want to consider several eigenvalues at once. So, but in order to have a chance of saying anything, we have to have a fusion rule which satisfies this. That if you have two eigenspaces with different paired eigenvalues, then their product is 0. Okay. And so this rule doesn't mean anything unless S circle has at least 2 elements. And then we ask for the usual fusion rules, this and this and this. Number 3 only says that this is included in A0, A plus A1 of A. That's intentionally weaker than HRS. And 4 is also standard. That A mu nu eats up A0 and A1. So the reason, the motivation for these particular fusion rules is so that this will be 2-graded algebra. And actually, I think that's misleading. I think each part has to be graded also in here. So an axial algebra is an algebra generated by axes. It's finitely generated if X is a finite set, and A is n-generated if X has n elements. And of course, anybody who's worked in axial algebras knows that saying A is finitely generated is a very treacherous statement because you would like A to be finite dimensional. But that's one of the big questions in axial algebra theory. So now, instead of using primitive axes, we're going to have weakly primitive axes, which means that the two-sided 1-1 eigenspace is only the multiples of A. But you could have one-sided 1, 0 or 0, 1 eigenspaces, and it will still be weakly primitive. It just won't be primitive. To be primitive, everything, the only time that one occurs, it has to be a multiple of A. Okay. So when I write we, that means you of and I. We've worked on this for several years, and we showed that when you have mu nu or nu mu, then I'm sorry, when you have one left and right eigenvalue, then you have this situation with mu plus nu equals 1. We believe that weakly primitive axes are correct. Well, I hope to convince you that in the course of the hour. Of course, in the commutative case, weakly primitive is just primitive. Okay, and so we call A weakly primitive, etc., if the axes are of that sort. And similarly, a weak PAJ. J sort of means Jordan, but what it really means is satisfies diffusion rules. Whenever you see J, it means that the algebra satisfies diffusion rules. So primitive, a weak primitive axial algebra satisfying the Jordan. Satisfying diffusion rules. And then A is type S if each axis is an S axis. Okay. So these just are analogous. And a CPAJ will be a commutative PAJ. So CPAJs are sort of what the standard theory might be. Okay. It's convenient to talk about the axis 0, even though it's not very pleasant. Because if you want to build up inductively, sometimes you have to include 0. So that's the trivial axis. So in other words, we'll call 0 B the degenerate axial algebra generated by A equals 0 and B. That's just FB. Okay. And this is just a comment that an element will be an A1 of A plus A0 of A if and only if AZ is an A1 of A. And that's it's trivial, but it's useful. Here's another useful observation. Since we're allowing all these eigenvalues, we want the option of limiting them. And in fact, if you take a subset of the set of eigenvalues, you will get a subalgebra of A. However, you don't know, so A will be in there, but B isn't. And you don't know whether you get an axis, another axis. That's a question that one has to cope with. Okay, so here's some well-known examples. I think in the seminar, you've probably seen many more examples. Commutative primitive axial algebras are very well studied by members of this audience. And in their seminal paper, they characterized two generated of this form, and they all have dimension at most 3. For a sort of interesting example, out of the box, you can take semigroups, and a semigroup algebra will also be of this form. It'll be associative with the left and right or the band. The band is that semigroup, and that has right, left, and right eigenvalues 0 and 1. But diffusion rules fail for band algebras. So if we're going to study them, we have to be willing to forego the fusion rules, or else modify the definition of the band algebra. In fact, you can't have everything. And in an associative algebra, the idempotents have eigenvalues 0 and 1. So you won't get anything interesting from the point of a multiplicity of eigenvalues. Okay. So our goal is to find a theory that contains much of the commutative theory. So of course you start with Miyamoto involutions. And you see, this has nothing to do with commutativity. All it has to do is any two-graded algebra has an automorphism just by reversing the sign of the negative part. So you can get a Miyamoto map just by taking one part and negating it. You don't know whether it's multiplicative though. That's a problem. So these are some properties of the Miyamoto involution. I'll skip that. So a Miyamoto involution is a Miyamoto map, which is an algebra automorphism. And if you have the fusion rules, you get a Miyamoto involution. And as I said, it's just an abstract property of two-graded algebras. Okay, so the first question I want to raise, which we don't know the answer to, is what criteria do you have to impose if you don't have the fusion rules? What criteria do you have to impose to get a Miyamoto involution? And I think that would be interesting. In fact, when A does not satisfy the fusion rules, we don't even know if B is an idempotent. But we're going to be assuming that A satisfies the fusion rules because otherwise it's too far. Okay. So then you can define G of X, the group of automorphisms generated by Miyamoto involutions, and the same beautiful theorems that hold in the commutative axial algebra also hold here. It's very important. Anybody who wants to study spanning has to use these because it's a way of going from generation to spanning. So here's the theorem. If you have an axial algebra generated by a set satisfying the fusion rules, they only need to be weakly primitive axes. Then A is spanned by the closure. That's applying all the group of Miyamoto involutions to X. If W is a subspace containing X, which absorbs multiplication, then it's all of A. I'm sure some people in the audience are very familiar with this. And also the components are the sums of the components. Okay. And I didn't give much of a proof because the proof, as I said, mimics the commutative proof. Okay. And then another thing that's often used, so I'm talking about tools now, is Ceres. Now, we're going to define an axis to be left Ceres if it has this part of the fusion rules. But we're not assuming that A0 of A squared is contained in A0 of A. Okay. And but if you want to show that an axis is Ceres, if it's weakly primitive, you just have to show these two containments. That's very important because these two containments are sometimes a pain. But if you can get through them, then you can get through them all. So,
Louis, can I interrupt just you? Okay, so because I started on my computer, okay, just to see properly. So by axial, weak axial algebra, you understand an algebra with a spectrum 0, 1, and something else. So
yeah,
it's different in terminology. So it's like Jordan type or something else, or
right.
so it's not axial at all, not.
I'm sorry?
So, well, okay, so in the previous terminology, so axial algebra is an algebra generated by any fusion rules. Right
Oh,
now,
no.
okay.
We have these very specific fusion rules. I can go back to them. If I can find them. Yeah. We have these very specific fusion rules, which are very much like the Jordan fusion rules. Okay.
And number mu and ni are from a set 0, 1, and
S.
and
No,
okay.
actually, S doesn't include 0 and 1. 0 and 1 are treated separately. And S
Okay,
is
S could be
all the
arbitrary.
other values. Okay.
I
So
see.
yeah. And weakly primitive is that the 1 component has to be a multiple of A.
Yes. Okay.
That's all. That's the entire thing.
Thank you.
Okay, so we're back. Anybody, who has a question is welcome to ask. So thank you. So now with this weaker definition of Ceres, you have this y0 and z0 are the 0, parts. So since I didn't assume anything about the product, you have to have it in there. But if A satisfies the fusion rules, then this is in 0 and 1. So when you multiply by A, you get to A. So you get this equation. So this always holds when A satisfies the fusion rules. And so often in proofs, you don't have to worry about FA. So this weaker version is good enough. And I put down the proof. But if you don't mind, unless somebody wants to see proofs, I'm probably going to just show them for a few seconds and then go on. So we have the term A times x, y0, z0. And so we want to know when that is 0, because then we don't have to worry about that extra term. Okay. Or in other words, we want this. And you can prove this when you have a Frobenius form. And now a Frobenius form is just an associative bilinear form in this sense on an algebra. And if you have a symmetric Frobenius form, then in fact you can get that. Under this mild condition, which I don't know how to get around. Okay, but the usual Frobenius form is that when I'm even going to write it down here. No. Okay. Yeah, the usual Frobenius form is you write an element B. Okay, this pertains to what you were saying, Vladimir, that it's alpha times A plus B0, that's an A0, plus these other components pertaining to S. Now, the usual Frobenius form in the axial theory is AB is the projection of B onto A. So it will be alpha B. And of course, AA will be 1 in that case. So it's not 0. So in this case of the Frobenius form, we're okay. I just couldn't get around it in general. Okay. Now, as long as we're talking about alpha b, which is AB, so try to remember that these three values are especially important. Okay, 0, half, and 1. And it's logical because these are the three values that come up in Jordan algebras things. Okay, so in fact, we were talking about S, and for some reason, I hope this will become clear if I talk fast enough. For some reason, the commutative case and this case, where the sum of mu and mu equals 1, they're particularly important. Okay. And so if A is weakly primitive and B mu is 0, if, in other words, if you have no extra values, then of course the dimension of A is 2 and negative. It's not necessarily associative, but it's commutative. Okay, so let's start with dimension 2. Now, there's a completely general way of writing down an algebra of dimension 2. And let's assume it's generated by idempotency. So we want to see one is axial. Well, first of all, we know it's left and right eigenvalues. And we know that A is semi-simple, except in a certain degenerate situation. So normally it will be a semi-simple idempotent. And it will be an axis if and only if this equation holds for these coefficients. And similarly, B will be an axis if only if this holds. And when you put this and this together, oopsie, you have A and B axes if and only if one of the following happen. A is commutative, or what I said before, this special relation holds that the sum is 1. Okay. So A satisfies the fusion rules. So I was just saying about axes. Now let's get to the fusion rules. A satisfies the fusion rules if and only this happens. And B satisfies the fusion rules if and only if this happens. And so they're both satisfy the fusion rules and axes, you get this. Well, this is very well known. This is the characterization of the two-dimensional commutative primitive axial algebras. It had better be, or else we would be in trouble. So anyway, so that's the situation for dimension 2. It's completely known. So okay, and then I wanted to check about the idempotence. Okay, and so in the non-commutative case, you get this situation. This is very easy, but it might be less familiar because it's non-commutative. Now, when psi is not equal to psi prime in that setup for the last page, then you have a new idempotent, this, which is not an axis. So even in 2 dimensions, you come up with something interesting, something new. Okay. And so since we have something new, let's check its left and right eigenvectors. These are the left and right eigenvectors, so E is left and right semi-simple. And you can check the fusion rules, and so you get that. I'm sorry, these are the axis rules, right? A plus B times A minus B times A plus B. So E is an axis if and only if rho plus rho prime is 1. But then psi would be rho prime, so A would be commutative. But we started saying it's not commutative. So in this case, we have a semi-simple idempotent, which is not an axis. Okay, so that's interesting. Okay, well, inspired by that situation, one might try to generalize it to arbitrary dimensions. And so we can define this algebra, the algebra set of idempotents. You'll notice that this is very similar to what I had 3 slides ago. And so this set of idempotents actually spans the algebra, which is very nice. So it'll be finite dimensional if you have a finite set of idempotents. And if you take A to be x1, you can calculate the eigenvalues, left and right eigenvalues of A. And again, not sure that this, for a general talk, I should spend too much emphasis on that. Okay, the commutative case, if mu equals nu, so we have this thing. If mu equals nu, so that this is commutative, then for I equals 2, of course, you get that same two-dimensional algebra. For I greater than 2, it becomes more complicated. And the fusion rules are only satisfied when mu is a half. Okay, for other mu, we have primitive axes that fail the fusion rules. So that's the commutative case. And that's what one would expect, that we'll only get fusion rules for the half eigenvalue vectors. The non-commutative case is perhaps more interesting in this case, because now Yoav and I studied this earlier for mu not equal to 0 or 1. So actually, this is new only for mu equal to 0. And then you get the band, what I was saying before. And then you can calculate this ideal is this is sort of like an augmentation ideal or something. I mean, it's a square zero ideal generated by the difference of the idempotents. And it's in fact, it doesn't depend which I you use. Okay, so A is left primitive axial algebra of type 0, 1, which does not satisfy the fusion. Wait. No, it does. I'm sorry. Which does satisfy the fusion rules. Okay, so this is a new example. And then you can calculate the idempotents. And symmetrically, you can get the right zero band semigroup. And you can define this. And so what we wind up with is, for the extreme cases, we get sort of degenerate algebras, in the sense that they degenerate to associative algebras. It's sort of funny when you say they degenerate. Okay. In fact, in this non-associative theory, let me just put in, it's often the degeneration of associative algebras. Okay. So since we handled dimension 2, let's go to dimension 3. And that is really hard. Yoav and I have been working on that for half a year. And I'll tell you what we've done. This is, since the two generated first we wanted to take care of the two generated case before we go on to higher generation. So everything I'm going to tell you now for the rest of the hour is two generated. So okay, so let's assume from now on that B is written in this way. And recall this definition that I gave you at the beginning of S circle, S dagger. That's S dagger, that's the non-commutative part. And S bars, I don't think we're going to use. Okay, so since we have this decomposition for A, it's completely obvious what the eigenvalues, eigenvectors of A are. They just come from the components. But B is a completely different story. And so, and in fact, one of the challenges at this point is to be able to say something about the eigenvalue, eigenvectors of B. And we're very fortunate. I'm not sure how far I'll get with this, but they often wind up having the first two coefficients 0. So I'm going to define V to be the set of elements of A such that the first two parts are 0. Okay, I think that's clear. And then the eigenvalues of B, if you take those eigenvalues of B, or I'm sorry, eigenvectors of B contained in V, we're going to call that V rho psi. And we're very fortunate that one can often show that this is all of A rho psi, that all of the eigenvalues, I'm sorry, all of the eigenvectors are in V. Well, anyway, just one easy observation is that when you take B, all of its components are non-zero. Okay. So we want to check when B is an axis. So the two things to check, well, this is part of B being an axis that associates with A, and it's an idempotent. And just from that, you get some very nice results. You get, first of all, that the sum of the squares weighted by the difference of mu and u are 0. So this only makes sense. This only is, I mean, it makes sense all the time, but it's only useful in the non-commutative case. And also this. This is very nice because this shows you when alpha b is 0 or epsilon is 1, epsilon is the sum of mu and u. Or when mu equals nu, this difference is 0. Okay, so I'll probably get to that. And you also get this result. So when you multiply B0 by B mu nu, you still wind up in B mu nu. In other words, I don't know if B0 is idempotent, but this is an eigenvector. B mu nu is an eigenvector of B0, both on the left and the right. And this tells you exactly what it is. So, and then you have some more equations that you get by solving this. This is interesting because it says that if the B mu nu squared are contained, I'm sorry, in the span of A and B0, then B0 squared is in that also. So you get an algebra. Okay. Anyway, if these two equations hold, you get this, and these two equations hold, you get B being idempotent. And so I think I said that. So if B mu nu squared is 0, this in fact is B times B mu nu. So B mu nu is an eigenvector, and that's in V. So I was saying that the elements of V play a special role. In fact, this will be a square 0 ideal of A. And if alpha B is a half, then B mu nu is a half-half eigenvector. That's just the special case. So I don't know. This is this was an attempt to find out what annihilates B mu nu. I don't know whether we're going to have time to use it, but this this shows you two elements that annihilate B mu nu. Now, the point of this is that you know that all the B mu prime nu prime annihilate B mu nu by the fusion rules. And B mu nu squared is sometimes 0. We saw that. So in other words, this is the essential part of the annihilator of B mu nu, in a sense. Okay. What was 10? Oh, 10 was the equation that the weighted sums of the mu mu squareds at 0. Now, this is true if you only have one summand. But in general, you don't have that, and that's challenging. So if you only have one eigenvalue pair, other than 0 and 1, then in fact you know exactly what A is, and it's three-dimensional. And this generalizes the classical situation. When B is an axis, you have two more things to check. You want to check this, and you also want to check that with B0. And so you get these extra equations by associating B with B0 and associating B with B mu nu. You get these equations and these equations. And so I've thrown a whole bunch of equations at you. Those are all the equations which exactly say that B is an axis. So if we want to study the, so I'm going to pass over that. So if one wants to study algebras generated by A satisfying the fusion rules and being an axis, we have all the tools that we need. And so that's what we continue with. So, this is very fortuitous. If alpha B, that's the projection onto B onto A, if that's not a half, and if A0 of A is commutative, that's a very weak assumption. For example, A0 of A is FB0, then A0 of A is certainly commutative because B0 commutes with itself. So under that assumption, then B mu nu squared is in fact 0. And so we can use all of these good properties that we were gathering before. So but there's still some issues left with alpha B not a half. Okay, and I think I said this before, but I didn't write it down, that this equation holds under one of these three conditions, which are the three important conditions in a sense for us, or in often happening. Okay, what happens to alpha b is a half? Well, you still get something. B mu nu squared commutes with b zero. And in fact, the converse also holds, except for this exception. Okay. Well, B0 could be anything. If it happens to be 0, which it is in certain examples, there are only two classes. So we can completely characterize the situation where B0 is 0. One is the commutative case, where you just get a two-dimensional algebra. And in fact, it's the usual two-dimensional algebra. So it's not so interesting. You go back, you get back to HRS that way. And what if A is non-commutative? In fact, you have an arbitrarily large algebra, depending on the size of S. And it's a axial algebra satisfying the Jordan fusion rules. I'm sorry. A satisfies the Jordan fusion rules. I haven't said B. So this is the completely general algebra where B0 is 0 and A satisfies the fusion rules. And this is a square zero deal. I'm sorry. I said I misspoke. Since B nu squared is 0, it is an eigenvector of B. So this does satisfy the fusion rules. I'm sorry. So this is an algebra of arbitrary dimension, a weak PHA of arbitrary dimension. And this completely characterizes the case B0 equals 0. So we'll assume B0 is not 0. And we'll assume A0 of A is FB0. And then just that very small assumption means that A, in fact, is spanned by these vectors. So its dimension is S plus 2. It's the size of S plus 2. Unless, yeah, that's exactly right. Okay. Well, in the past, we've seen that B mu nu squared is 0, gives us very good results. So we want to study that. Well, B mu nu squared has to, by the fusion rule of A, has to be of this form. And then you can prove this. So, so in fact, the ratio, so in fact, this ratio is in a sense fixed depending on mu plus nu. Okay. If alpha b is not a half, then in fact that epsilon dagger is independent of everything else. But if alpha b equals a half, it's more complicated and more interesting. As you see, alpha b equals a half is quite challenging. Okay. But even when alpha b equals a half, we have this fact. Okay. That b mu nu squared is here. Okay. What happens if we're fortunate enough that b mu nu squared is 0? Well, then you can project. You suppose you have a set S prime where this happens. then you can project down to what I call S natural, and you get an axial algebra. And A is weakly commutative, satisfying diffusion rules. And for each subset of S prime, this is a square zero ideal. And B projects down to an idempotent, so you have a real axial algebra. And yeah, B is an axis, in fact. And so it's natural to try to do an inductive procedure here and to remove one square zero eigenvalue at a time. And this theorem is the previous one. I just didn't get it notated. And what happens is you get what you expect. You have a decomposition, you have a B natural as an axis, you project onto eigenvectors. Oh, this is nice, that the eigenvalue of B mutat with respect to B, the sum is 1. Again, that comes up all the time. And that you get some more properties which are useful. And if B satisfies the fusion rules, then B natural satisfies the fusion rules. That fell off the slide here. So an example is one that Yoav and I looked at a long time ago with these relations. And then A is spanned by 3 vectors, where y squared is 0. You have these multiplications. And B0 itself is actually an idempotent. And I thought for a while that this contradicts the assertion of the theorem, but in fact, the theorem assumed that you don't have rho equals psi equals 1. So this situation would be a counterexample to the assertion of the last slide, if rho equals psi equals 1. And then I'm beginning to run out of time. If B satisfies the fusion rules, then A natural also satisfies the fusion rules. I told you it was had 2 axes, A and B natural. And conversely, you can lift the idempotents and the eigenvalues and the eigenvectors, but okay, before the but, so we're only going to add a 1 trivial extension, and then an extent on, if you repeat 1 trivial extensions, you have a trivial extension. So if you have a trivial extension, then you project down and you get an axial algebra satisfying the fusion rules. So you can reduce the study essentially to the commutative case. But there's one big problem. Okay, and maybe I'll end with, oh, well, let me give you this example. So this we call the S exceptional algebra. It's like what we had before, but it's a generalization. We're going to take this space and we're going to define multiplication in this way. And that will be a weak primitive axial algebra. And So that's our second example of an arbitrarily large example, non-commutative. And the alpha b is 0 in this case. So okay, so let me just say a few words. Since alpha b equals 0, that's good and bad. That means we have an example that we know about, but it also means we don't know much what happens with alpha b is not 0. And so, in fact, when alpha b equals 0, we can pretty much characterize the situation. And we're working on, so that happens here, and we're working on the case where alpha b is not 0. So let me, okay, that's the downside. And let me just skip to the end. So we have a lot of results for the fusion when B satisfies the fusion rules, but it's ridiculous to start talking about them because it would just I couldn't say anything meaningful in 2 or 3 minutes. And there is an axial graph, as in the commutative theory, and there's this Frobenius type bilinear form, which we're studying. And we do not have an example of a commutative two-generated weak PHA of dimension 3. We have a candidate, but we have not verified that it really is true. And then there are references. I'm not really experienced enough with the literature, but these are some of the major references that are relevant to our work. Okay. So thank you very much.
Okay, thank you very much. So let us give our speaker a round of applause for a very interesting talk. Any questions, comments?
I have a small question. So somehow for 20 minutes ago, you mentioned some example. So you said it's completely new, or it was some for any dimension. Okay.
Right.
Do you remember? Okay.
There are
So
two such examples. One is with what I was talking about then was with B0 equals 0, when
before, I think before. Okay. So my question is it some algebra you can characterize by, like it's quadratic algebra, satisfying some small degree identities or not? It's just an algebra, because it's seems like Clifford Jordan algebra. Okay, for myself. Okay, maybe I'm wrong. Okay, but it was some several seconds on the screen, but
right. I haven't considered its identities. It's sufficiently nice that you might be able to do that.
I just it was
I don't know. It's a very good question. I regret that I haven't thought about that. If you have ideas
Okay, if
about
I
that.
can make a comment, sort of, I have a project with my PhD student. We try to sort of act in the same way as a paper by Louis Youaff and on the Metz about forge-generated algebras of Jordan type. And we were trying to build explicitly the forge-generated baric algebra of Jordan type half. And by accident, I mean, that algebra actually has dimension 54 in all characteristics except 3. But by accident, we also constructed a non-commutative algebra of dimension 55, one higher.
Oh, really?
And that's also a very nice algebra because sort of left action of all x's is just normal Jordan fusion law, and the right actions get an extra eigenvalue -1. So there is this one-dimensional ideal on which all x's act as -1. But other than that, it's very so it looks very similar to what you were describing, like an example. So
Yeah,
non-commutative, very large ideals there. There is. So an algebra has a one-dimensional ideal modulo it is just a good, sort of commutative algebra. But on this ideal, on the left, all x's act as a half, and on right, they act as -1.
but you said these are 4 generated?
Yes, it is 4 generated, baric, so it has a very large ideal for dimension 1. So all values of the Frobenius form are equal to 1. So that's, it is the easy case. That's why we try to understand it explicitly.
Uh-huh. Where can I find this? I saw your work about
No,
the
it is,
intermediate.
it will be in the PhD thesis. I have a little bit of a draft, and we just build it in a computer. I can send you the code if you want to run and get the algebra.
Oh, well, I'm challenged in that way. But if you have a description of the algebra, I'd be very interested to try to compare it with what we've been doing. Yeah. Thank you very much for that comment.
So, a general question. Okay, so those commutative axial algebras, they are very well known, like connecting this nice group theory and automorphism to that. Okay, so what is the specific for non-commutative case? Do we have 2 different sites, or what we have?
I really don't know. I'd really be interested if somebody.
Okay. So it was not a starting point to get some polarization of this, not?
I'll tell you, for me, maybe for Yoav too, but he can speak for himself. The inspiration was having a beautiful set of axioms in the HRS paper that we wanted to see how far we could push it. How far, so we're thinking of it more in the terms of Hardy, rather that you want to find some elegant structure. But the hope, of course, is that if the structure is elegant enough, then it will have applications. But
okay,
anybody who could find applications, would be very grateful.
And I have another question. So excuse me, maybe it's too much. Okay, but you mentioned some ideal generated by differences of idempotence, because I met it before in different contexts. Okay, what is related, because it was too fast maybe. Okay, so did you mention that, right?
Yeah,
so
yeah.
An idea.
It was in one of the examples. It looks a bit like it's a square central, and it's a square zero ideal that
Okay.
mods out of codimension 1. So it sort of looks familiar, but other than that fact, it comes up in the commutative theory too, in certain examples. But that was in that first uniform example that we had the square zero ideal.
Okay. Any further questions or comments? If not, let's again thank our speaker today.
Thank you very much for the invitation. I appreciate it.
Thank you very much. Nice talk.
Well, I guess one of the organizers should tell us what will happen next.
It will be Tuesday. At least.